I'm going to show you a quick example of how to use the principle of absolute convergence, which says if I have some series and I take all of my terms and I make them positive, if this modified series converges, then my original series converges as well. I want to note the converse isn't true. If you modify your series in this way and it diverges, you don't know what happens to your original series. Here's an example. I have this series, and I'd like to know whether it converges or diverges, but the problem is all the tests we know only work when your terms are positive. The ratio test, you need your terms to be positive. The limit test, the comparison test, you need your terms to be positive. So what we're going to do is we're going to modify this series, and we're going to make a secondary series where I just take the absolute value of all of my terms. So this minus 2 to the n, that's just the same as 2 to the n, and factorial was positive to begin with. So I'm going to consider this instead. And if I can show this converges, then I can conclude that my original series converges. If I show it diverges, then I need to try something else. Okay, now this one has a factorial in it. Factorials usually play nice with the ratio test. So let's try that. I'm going to set up my limit, and I'm going to clean it up to make it easier to understand. Now 2 to the n plus 1 divided by 2 to the n, that's just 2. And n factorial over n plus 1 factorial, well remember I'm multiplying 1 times 2 times 3 times 4 all the way up to n on the top. And on the bottom I'm multiplying 1 times 2 times 3 times 4 up to n and then also n plus 1. So the only thing that doesn't cancel is that n plus 1. Now this limit, when n gets real huge, is just going to be 0. And since 0 is less than 1, by the ratio test, I see that my series, this green series, is going to converge. Now I can just use the principle of absolute convergence. For my original series, because when I take the absolute value, I get rid of these negatives. When I do that, it still converges. That means that this series also converges. And in fact, we say it converges absolutely. If you try to use absolute convergence and it doesn't work, usually you can get away with the divergence test. Here's another series that has sometimes negative terms. So I might want to try seeing what happens if I make all of these terms positive. I might try the ratio test again. And after simplifying, I get something like this, which is 2 times 1, which is 2, and 2 is bigger than 1. So by the ratio test, this particular series diverges. Now it's possible that when you take the absolute value, that modified series diverges, but your original series converges. So we can't just say, okay, it somehow absolutely diverges. That's not a thing. We have to do a different test. But in this case, this is a pretty easy one. We can just use the divergence test. These terms that I'm adding are not going to 0. Remember, exponentials grow faster than polynomials. So as I put in bigger and bigger values of n, these terms are going to go to plus infinity and minus infinity. I'm going to be adding a million and then subtracting a million and then adding a billion and subtracting a billion. So the sum is definitely not approaching any one number. So to use the divergence test, we note that the limit as n goes to infinity of minus 2 to the n over n squared does not exist. So my series diverges. And we didn't actually get to use our absolute convergence test. You can't use the absolute convergence test to show that this kind of a series diverges.